Hi everybody, this is our pathophysiology video on hematology and oncology. The first thing we're going to talk about is the process of hematopoiesis. So you've probably seen this chart before, but I'm going to give you some details on how we get from the hematopoietic stem cell, or HSC, all the way down to all these cells that are found in your blood. So in general, hematopoiesis occurs in the bone marrow. That's where you will find the HSC, and HSC is a quiescent cell, meaning that it's in a resting state for most of the time and only wakes up to divide every couple of months, giving us our myeloid progenitor and lymphoid progenitor. So the myeloid progenitor responds to a variety of growth factors and other molecules that will cause it to differentiate into all of these cells, eventually giving us our granulocytes down here, red blood cells, and platelets. I'm only going to talk about 3 of these factors that seem pretty important. First, we have thrombopoietin, or TPO. TPO is secreted from the kidneys and bone marrow, and it will bind to all of the cells and the platelets in this box. It's secreted at a pretty constant level and also binds to all of these cells at a pretty constant rate. So that means if somebody has a low platelet level, there's going to be more free TPO available to bind to the cells earlier in the line, thus stimulating them to differentiate into platelets, and then that will restore their platelet level. Second, we have erythropoietin, which is secreted from the kidneys when they sense low levels of oxygen in the blood. So if more erythropoietin is being secreted from the kidneys, you're going to get differentiation of all of these progenitor cells into red blood cells. Thirdly, we have granulocyte colony stimulating factor, or GCSF. This factor is secreted by macrophages, endothelial cells, and fibroblasts. So it's secreted at a pretty constant level, but the level will be increased if there's an infection, injury, or inflammation. So if you have any of those 3 things, you're going to need more of these cells to respond. So it makes sense that inflammation will cause more GCSF to give you more differentiation into the granulocytes. So then we have our lymphoid progenitor cell. This differentiation process is pretty complicated. So I think the important things to know here are that B cells and natural killer cells both develop in the bone marrow, whereas T lymphocytes will start in the bone marrow but migrate to the thymus where they will finish their maturation. So B cell for bone marrow and T cell for thymus.
So now we're going to review the formed elements of the blood. Formed elements of the blood can be separated into 3 categories: the red blood cells, or the erythrocytes, the platelets, or the thrombocytes, and the white blood cells, or the leukocytes. To distinguish these from one another, we will use a blood smear and look at it under the microscope. Red blood cells have a role of binding oxygen from the lungs and delivering it to the peripheral tissues. As you can see in this image, we have red blood cells. They appear as a biconcave disc without a nucleus. The lifespan of a red blood cell is about 120 days. The second formed element we will talk about are the platelets. The platelets assist in blood clotting with the help of coagulation factors. They are composed of cell fragments without a nucleus and appear as purple granules, which are from the precursor bone marrow cells, also known as megakaryocytes. And here you can see the purple platelets. The lifespan of a platelet is about 7 to 10 days. The third of the formed elements are the white blood cells. The white blood cells play an important role in immune regulation. They're responsible for fighting infection. The white blood cells are separated into 2 categories based on how they appear under the microscope. Granulocytes, the nucleus appears as many lobes under the microscope, so it will look segmented. Whereas the mononuclear cells don't appear that way. The nucleus appears as a single lobe. Granulocytes are separated into neutrophils, eosinophils, and basophils. Whereas mononuclear cells are separated into monocytes, which will further differentiate into macrophages, and lymphocytes. Let's further discuss granulocytes. Remember, they're named for their multinucleated appearance under microscopy, as well as because they appear to have granular-like material within their cytoplasm. Neutrophils are phagocytes. They engulf foreign invaders as part of the immune response. They're the first responders of all white blood cells, and they're present in acute infections, primarily that of bacterial and fungal infections. On microscopy here we see that the neutrophil has 3 to 5 lobes, and there are lilac-colored granules within the cytoplasm. The lifespan of a neutrophil is only hours. Eosinophils play a role in chronic immune responses, primarily that of parasitic, asthmatic, and allergic reactions. Under microscopy here we see that there are 2 lobes of the nucleus with reddish granules in the cytoplasm. The lifespan of an eosinophil is only 2 to 5 days, but cytokines can extend their lifespan up to 14 days. Basophils are present during allergic reactions. They're responsible for releasing histamine and alerting the body that there is a foreign substance. Under microscopy here we see that the basophil has a massive amount of dark blue granules within the cytoplasm. This makes the nucleus very, very difficult to see. Basophils have a very short lifespan. Mononuclear cells consist of monocytes, which are precursors to the phagocytic macrophages. This differentiation occurs when monocytes leave the blood and enter tissues to become macrophages. Under microscopy here we see that the nucleus of a monocyte appears to be kidney-shaped. There's also a light blue cytoplasm. It is also important to note that monocytes are the largest of all white blood cells in size, and they can live for many months. Lymphocytes represent T cells, B cells, and natural killer cells, which are responsible for the production of antibodies and for the immune memory. They arrive later in the inflammatory process, behind neutrophils. Thus, lymphocytes are elevated in long-term infections, primarily that of viral. Under microscopy, you see a large round nucleus with a scarce cytoplasm. An active lymphocyte is when an antigen has been bound, whereas a resting lymphocyte is when an antigen has not been bound to the lymphocyte. Figure E shows a resting lymphocyte, which is much smaller than figure F, which shows an active lymphocyte. So in other words, the only difference between resting and activated lymphocyte on microscopy is size. The lifespan of a lymphocyte is many years.
Video discusses the pathophysiology behind heparin-induced thrombocytopenia. But first, let's review the coagulation cascade and how heparin is involved. In the coagulation cascade, the intrinsic and extrinsic system interact together. Heparin is responsible for activating antithrombin 3, which then inhibits factor 12A, 11A, 9A, 10A, and thrombin, which inhibits the formation of fibrin. Fibrin is responsible for allowing platelets to bind together. So platelets produce something that is called platelet factor 4. Platelet factor 4 is trying to stop heparin, which in turn stops antithrombin 3 and promotes coagulation. Platelet factor 4 does this by binding to heparin. This is called a hapten, which is responsible for production of antibodies that will then bind to it. So this new hapten, platelet factor 4 and heparin, are going to stimulate the immune system, which is then going to produce an antibody, IgG, which will then bind to it. This in turn is going to activate platelet production, which then produces more platelet factor 4. More platelets, of course, cause more blood clots, which are going to use up all the platelets. This in turn results in thrombocytopenia, also known as a decreased count of platelets, and put the patient in a hypercoagulable state. This is why you can have heparin-induced thrombocytopenia.
This brief video is on ITP, immune or idiopathic thrombocytopenia purpura. So what is ITP? ITP is a disorder which causes antibody-mediated platelet destruction. So what does that mean? In the body, we have platelets that help us to form clots. For some reason in ITP, something triggers the immune system, such as a virus, that causes the body to recognize the platelets as foreign. Antibodies are put on the platelets, which mark it for destruction in the spleen by the macrophages. So the macrophages see these platelets with their antibodies on it as the enemy, and they attack the platelets, and kill them off until the platelet count is low. So even though in ITP they have low platelet counts, they can still clot. They do still have platelets. They're just very low. Severe bleeding is very rare in ITP because the platelet count would have to be very low. It would have to be somewhere in the 10,000 range, which is rare. And this concludes the video. Thank you for watching.
So now we're going to talk about the basic processes involved in carcinogenesis. So here's kind of the basic overlying process. You have normal DNA that acquires mutations in genes, and these have to be non-lethal so that the cell can replicate with these mutations. That's going to proliferate and then cause an eventual neoplasm. So the most common cell types that are affected are your tumor suppressor genes, which are normally involved in the regulation of cell growth, your proto-oncogenes, which are involved in normal cell growth in the cell cycle, and if mutated, they become oncogenes and are then capable of neoplasm production. Once they do become oncogenes, they start synthesizing and secreting their own growth factor receptors, and other cell proliferating substances. You also have your apoptosis genes and DNA repair genes. So those are the most common 4 types of genes affected. So for a cell to go from normal to malignant, these 6 things have to be present. So they have to be self-sufficient with growth signals. They have to evade apoptosis, replicate without limits, have defective DNA repair, be capable of angiogenesis, so supply themselves with blood supply vasculature, and invade surrounding tissue. And just of note, UV radiation and smoking, we know, are 2 of the big causes of that initial mutation in cellular DNA.
So next we're going to talk about the role of the liver in the coagulation process. So the liver is the site of production for both clotting factors and anticoagulant proteins. And so the clotting factors that it produces include factor 1, 2, 5, 7, 8, 9, 10, 11, 12, and 13. Or you could just remember that it produces all of them except for 3 and 4. And it also produces anticoagulant proteins such as protein S, protein C, antithrombin, and plasminogen. And so the liver really just helps regulate coagulation and fibrinolysis by clearing clotting factors using these anticoagulant proteins.